What if I told you most of the matter in the universe wasn't in stars, wasn't in galaxies, wasn't in black holes? It was hiding in the dark. For decades, astronomers ran the numbers, and half of normal matter was missing. Not dark matter, not something exotic, the same atoms that make you. Gone. And we didn't find it by seeing it glow. We found it by watching millisecond flashes from across the universe get stretched, delayed, distorted. Because the universe isn't empty. It's threaded, woven, structured. And we just turned the lights on. You clicked for the universe's hidden web. Good call.
In the next minutes, we'll track how astronomers went from theory to first glimpses of the vast gas filaments threading galaxies together.
The universe all around us is filled with galaxies, so it's kind of natural to say, would there be a final galaxy? If you traveled far enough away, would you finally be at the very last galaxy in the universe, looking out into empty space?
The key to understanding the edge of the universe is that light travels very, very fast, but not infinitely.
Even the sun, 93 million miles away, the light takes 8 minutes to get to us.
When you look out at the stars, we start to think of distance in terms of light years, because it takes years for the light to get from those stars to us.
But here's the twist. We'll separate the invisible dark matter scaffolding from the luminous gas riding on it, so you finally see which part does what. What did we miss for decades, and how did we find it without seeing it directly? Stay with me as we follow the clues scientists chase to bring the cosmic web into focus, and why solving that puzzle clarifies where stars get their fuel.
It takes time for it to get from one place in the universe to the other.
You open the curtains, light fills the room. It doesn't seem to travel at all. But over the vast distances of the universe, you actually notice this travel time.
And then when you look at galaxies, then you're talking about millions or billions of light. You can't really even find a galaxy too much farther away than that, because the universe is only 13.8 billion years old, and it takes a certain amount of time for galaxies to even form.
Half the ordinary matter went missing, not the exotic dark stuff. The same protons and neutrons that build you, your phone, and every star you've ever seen. If that matter didn't end up in stars, planets, or the bright parts of galaxies, where did it hide? Start with a definition. When astronomers say baryons, they mean normal matter, particles like protons and neutrons that lock into atoms, dust, and gas. Early universe physics sets a budget for how many baryons should exist. The microwave afterglow of the Big Bang encodes that number, and so does the ratio of light elements forged in the first minutes. Those independent yardsticks agreed on a value. Yet when telescopes counted baryons in the nearby universe, stars, cold gas, glowing nebulae, and hot plasma, we kept coming up short. The shortfall wasn't a rounding error. Teams tracked stellar masses in galaxies, weighed clusters by how their gravity bent background light, and measured the X-ray glow from their superheated gas. Add in the cool gas in galaxy disks and the warm halos surrounding them, and the inventory still lagged by a stubborn fraction. Depending on method and distance, somewhere between about a third and half of the expected baryons refused to show up. The hunt stretched for decades because every obvious container had been checked.
So we're not going to find too many more galaxies farther away than this.
If things are far enough away, there is no way that light can get to us in the age of the universe. What this means is there's a hard limit to the edge of the universe that we can see.
If you look in any direction at all, you get all the way back to when there were no stars, no galaxies, nothing but very, very hot gas. And that sort of forms a shell around us.
Edge of our universe, the very furthest thing that we can see, is one of the earliest relics of the formation of the universe itself. That is the cosmic microwave background.
So theorists drew a different map. Gravity doesn't pull matter inward at random. It amplifies tiny ripples from the early universe into a pattern of nodes, filaments, and voids. Invisible dark matter dominates the mass and sets the framework. Normal gas feels that pull and streams along the dark skeleton, collecting into long filaments that span millions of light years. Between galaxies, this material forms the intergalactic medium. It's not empty. It's just thin, spread out over an enormous volume. Here's the key distinction. Dark matter shapes the roads. Gas is the traffic. Dark matter doesn't shine, but it builds the landscape. Gas can shine, but only under conditions that make it bright, when it's dense, very hot, or excited by intense radiation. Most of the time, the intergalactic gas is too diffuse to glow strongly. It heats to hundreds of thousands to tens of millions of degrees through shocks as matter falls into the web, but at those low densities the light is faint and easy to miss. Computer universes help fill in the guesswork. Large hydrodynamic simulations. Think projects that evolve billions of particles and fluid elements under gravity, gas physics, and feedback from stars and black holes, consistently produce a lacework of filaments. In these runs, a big share of the baryons end up in a warm-hot phase, often abbreviated WHIM, with temperatures between about 100,000 and 10 million degrees. That range is too cool to blaze in bright X-rays like the cores of clusters, and too warm to show up in the common optical lines we're used to seeing in nebulae. We also trained our telescopes on the wrong targets. Surveys optimized for galaxies find galaxies. Exposure times, filters, and selection, all tuned to high surface brightness and compact sources, push us toward the densest peaks. The web's bridges, wide, dim, and diffuse, were often washed out by background noise or filtered out by data pipelines designed to avoid false positives. And that matters for more than neat maps. Galaxies grow by eating. They need a steady inlet of fresh gas to keep forming stars over billions of years. If the only reservoirs were the obvious ones we already knew, star formation would have choked off long ago in many systems. The filament network offers both supply lines and staging areas, delivering fuel and setting the pace of growth. So astronomers flipped their approach. Instead of treating the space between galaxies as an empty backdrop, they treated it as the main stage. They aimed at the faint, warm-hot gas and filaments, where the budget said the missing matter should sit. And once you target the right phase, you can use a very different tool to read it. Bursts of radio waves that turn the dim margins into a measurable ledger. Fast radio bursts. How do you see something that hardly glows? You don't. You count what it does to the light passing through it. That's the trick astronomers use when the target is too faint to image cleanly. Instead of chasing the glow, they watch how background signals get stretched, delayed, or nibbled by atoms along the way. The faint web becomes visible not by shining, but by leaving fingerprints on brighter beacons that cross it. Enter fast radio bursts. These are millisecond blips of radio light that fire from distant galaxies and cross billions of light years before our antennas catch them. They arrive as single pings or as repeating taps, and they cut through the intergalactic medium like sonar pulses through water. Each burst is short, but it carries a detailed record of how much free electron soup it swam through. So the web isn't just detected, it's measured with densities, temperatures, and distances tied to real objects. That sets up the next question. If these filaments hold the fuel, how do they feed galaxies and set the pace of star formation over time? Dark matter lays the frame, a silent grid setting where gravity gathers. Through that scaffold, faint ionized gas flows, threading filaments that ferry fuel into galaxies. Those streams explain how star formation keeps going and where the missing baryons settled, spread across warm hot channels rather than locked in bright islands. So when you hear about a new FRB catalog or a quasar absorption survey, treat it like someone turned up the house lights on the universe's plumbing. Share that with a friend who thinks space is empty. They'll see circulation, not void. The universe isn't a void. It's a web, coming into focus now.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.